Hello YouTube. So in this video I want to talk about a problem for scientific realism that arises from the nature of representation in science. So first of all, scientific realism. Scientific realism is the view that our best scientific theories provide approximately true descriptions of the world. I have a whole series on scientific realism if you want to learn more about it, but the basic idea is fairly straightforward, right? It's that science is trying to tell us how the world works, and it is at least sometimes successful at that. So when you look at the best theories of the mature sciences, theories that are very well supported by evidence, that have achieved a consensus among the relevant scientific community, we're justified in believing that those theories are at least approximately true. I mean, of course, we don't know everything, right? Like any theory is going to be incomplete in various ways. There's probably going to be some simplifications, some idealizations, but by and large, science is telling us how the world works. It's getting at what the facts are. That's basically scientific realism. So, okay, so a general point then is that whether or not a particular claim is true, or whether or not a particular theory or model is accurate, is going to depend on, what that theory or model represents, right? So whether or not T is true or accurate is going to depend on what T represents. So simple example of this, think about a statement like grass is green. So you can imagine, like taking the proposition, grass is green, or you can even imagine like a little kind of model of the world, right, where we have grass and then it's given a particular colour. Well, grass is green is of course true, but what makes it true is it's partly dependent on the meanings of those statements. So what makes it true is partly the fact that grass refers to a particular type of thing and green picks out a particular type of colour. You can imagine a language like English, but where green refers to what we would call blue. Obviously, in that language, if somebody was to say grass is green, well, that would be false. You'd say, well, no. I mean, the sky is green, right? But grass is not green, right? You've misdescribed the color. So obviously, whether or not a sentence is true is going to depend partly on the meanings of the terms. Similarly, if you have a theory or a model, whether or not that theory or model is accurate is going to depend on what the elements of that theory or model represent, right? Like if I present a particular model of the sun and maybe I sort of show that it has a core and then a radiative zone and then a convective zone and so on, well, I can say that that model is accurate, but like whether or not that model is accurate is going to depend on what all of these elements are actually representing. If you took the model as representing something completely different, like if you have, say, the core of the sun, and you took that to represent, I don't know, like some sort of biological algae, well, obviously then that model would not be accurate. So again, I think it's a fairly trivial point, right? Like whether or not a statement is true, right, is going to depend on the meanings of the terms. Whether or not a model is taken to be accurate will depend on what the elements of that model represent. Now, representation is something that requires both a source and a target. So think about a picture, say like a photograph of Frank Zappa. The source is the photograph itself. It's the physical object, like I might hold up a physical object that's the photograph. That's the source. And then the target in this case is a particular human being, right? So we say that this picture or this photograph represents Frank Zappa. In this case, the photograph is the source, the target is Frank Zappa. Obviously, the target might not actually exist. If it's a picture of a unicorn, say, then, well, there are no unicorns, so we think. But at the very least, you're going to have a source and then a purported target. So there's the sort of medium of the representation and then the thing that you're trying to represent. Okay, so with that said then, here's the issue. When you take the representations that are produced in science, when you look at the sort of models and theories or even, images that might be produced by instruments, say like the output of instruments. When we analyze these as representations, we're often going to be unable to specify a target for them. So there's a kind of underdetermination or indeterminacy in the sense that there are going to be just a sort of infinite number of different targets that are, that could be assigned to that representation in a particular context. So here's an example to show how this works. So let's take, for instance, fMRI images. These are relatively simple products, right? So we're just talking about the kind of outputs of fMRI machines, that we use to do brain scans and things. So the outputs of fMRI machines, these are just images, right? Like I can just show you an fMRI image, and then we can ask, okay, what does this represent? So we're not even talking about, the more sophisticated things like theories and models. Let's just take an image. Okay. How does fMRI work? It's worth kind of explaining a little bit of the background on this. So basically, with fMRI, I think this is the case. I might be getting a few of the details wrong, but it doesn't really matter. So, the precise details don't really make much of a difference to this. But with fMRI, the way that it works is that you have, protons have a small magnetic field. And if you place a bunch of protons in an external magnetic field, they will orient themselves either parallel or anti-parallel to that magnetic field. But they're not going to line up perfectly. Instead, they sort of precess around an axis. Now, if you apply a pulse of radio frequency radiation that is in resonance with the natural rotation frequency of the protons are going to be forced to rotate in phase together. And all of these protons rotating in phase produces a detectable radio signal. So then when the external radio frequency pulse is terminated, well, the protons are going to go out of phase. They're no longer going to produce a detectable radio signal. Now, the key to fMRI is that the rate at which protons go out of phase is dependent on their environment. In particular, the rate at which they go out of phase is dependent on whether they're in oxygenated or deoxygenated blood. So you can use different rates of radio signal decay to distinguish between oxygenated and deoxygenated blood. And then, since we know that oxygenated blood is going to be found in regions of higher neuronal activity, well, we can use this data to figure out what's going on in different parts of the brain, right? Basically, we use these radio signals produced by the decay of these rotating the protons. As the protons go out of phase, right, the decay of that radio signal will tell us areas of oxygenated and deoxygenated, higher, like more or less oxygenated blood in the brain, and that's going to tell us regions of higher neuronal activity. That is the basic idea. Okay, so that's what's going on when an fMRI image is produced. So now the question is, okay, so we have this image. What exactly is represented by this image, right? When I produce an fMRI image, what does that image represent? And, clearly, there's a huge number of things we could say here. So when I hold up an fMRI image, you could say, well, this represents radio signals. That's what the instrument is directly detecting in some sense. So maybe it represents radio signals. Maybe it represents patterns of proton precession, right? So the protons are manipulated by the machine to produce the radio signals. Maybe it represents that. Maybe it represents regions of oxygenated blood. Maybe it represents regions of higher electrical activity. Maybe it represents a brain, like a particular brain. Or maybe it represents the brain, just in the abstract, right? So I could take an fMRI image and I could just say okay, this is a representation of the human brain. Or maybe it's a representation of the schizophrenic brain. If I have put somebody with schizophrenia in the fMRI machine, I might say, oh, this image that's being produced is like a typical example. It's like an exemplar example of a brain with schizophrenia. So this is the schizophrenic brain. Now, look, obviously the sort of so the representation that is assigned is going to be probably dependent on context. If you're a doctor, then you're probably going to take the image to represent the brain of a particular patient. Maybe you're looking for some sort of pathology in the image. If it's a neurophysiology class, maybe you're going to take it to represent the schizophrenic brain. But then even within that context, different individuals may have different interpretations. Those who understand fMRI technology might take it to represent regions of oxygenated blood. Those who don't might take it to represent, just a brain or something. But the key point is that in the case of this image, we can see, okay, there's this pretty radical indeterminacy, right? Like if I ask, well, what does this image represent? There's just a huge number of things. There's a huge number of representations that you could assign to that. And the same point is going to hold for all of the sorts of representations that are produced in science. So like I could have, say, a particular model, and I might say, well, so like a model of the sun, right? Let's say I try to produce a model of the sun. Well, what that is actually going to involve is, a bunch of equations. I mean, that's one way that you can present a model, is as a bunch of equations, or maybe it's like a picture, right? It might actually be a diagram or something like that. But if you ask, well, what does this model represent? Does it represent the sun, or does it represent stars of a particular mass, or maybe like F-type stars? Or is the sun a G-type star? Anyway, it doesn't matter. Right, the point is, like, does it represent the sun? Does it represent a particular type of star, etc.? Or something like the Lotka-Volterra model in biology, right? Like, what is it that is represented by that? Is it you could use it to represent some specific biological population, or I could use it to represent predator-prey interactions just in general, or I might even use it to represent certain types of relationships that bear the same kind of mathematical structure even beyond biology, if there are such things. Maybe there's like similar relationships that are exhibited by interactions in computer programs or something. But in any case, any representational item is going to exhibit this radical indeterminacy. There's going to be many, many representations that you could the many targets of the representation. So whenever you present a representation, there's many potential targets. Now, one obvious thing we can say here is, well, okay, there's this indeterminacy or underdetermination if you're talking about the representation just in itself. I mean, like if I show you an image or I present a model and I'm like, well, what does this represent in the abstract? Maybe there's not really anything you can say. But this indeterminacy is not going to arise if we're talking about how this representation is used by a specific individual person. Or at least we might think that it's not going to arise in that case. So the reason is that we can just ask the individual what they have in mind. So if there is somebody who has produced an fMRI image and I ask them, well, what do you take that to represent? They can specify. They can tell me. They can say, oh, well, this represents regions of oxygenated blood in the brain or something like that. We just ask an individual, okay, what is the target of this representation? And that seems fine. There are actually, even in the case of individuals, there may still be some indeterminacy there. I mean, if we go in for things like Quine's indeterminacy of meaning or whatever, so maybe this doesn't solve the problem, but at least plausibly, right? This is one plausible path to solving this issue, is to say, well, we can specify a specific target of a representation as long as we're talking about how that representation is being used by a particular individual. So the problem is, I think we now have a kind of dilemma then, which is this. So if we are realists, then it looks like we're going to want to take the products of science as representations. Because in order to say that, an image or a model or a theory is accurate, we have to say what it represents. So if we're realists, we're taking a kind of representational perspective on science. But in order to take the products of science as representations, it looks like we're committed to a kind of an extreme sort of individualist view of science, where we sort of have to say that, theories, models, data, these are things that occur in the heads of specific individuals. But this kind of view might be quite implausible, because we often think of science as a kind of collective activity, and we often think of the products of science as being collective in the sense that, so like we will talk about, say, Darwinism in general as a general theory that is shared by many scientists. We can ask how some piece of evidence bears on this theory. So when we ask like how some data bears on the theory of Darwinism, it doesn't seem like we're just talking about, data as it is interpreted by a specific scientist, and the theory as it is interpreted by a specific scientist. We're sort of thinking of it in a more general sense, right? Like there's this general theory and general data that can be shared among many people. So we're sort of considering the data and the theory as being products of like the scientific community as a whole. More generally, in science, certainly today, with the rise of big science is performed by teams, like whole research teams, sometimes hundreds of people. In many cases, with many experiments, no one individual is going to be capable of performing the experiment. So if it's an experiment that involves, some, really sophisticated piece of equipment like a particle accelerator, sometimes not even one laboratory will be able to perform it. Like sometimes it requires coordination of teams all over the world. I think when we produced the image of the black hole, that required teams from like different continents, like all working together and analyzing the data and so on. Like, so no one individual knows enough. No one individual has the required specializations to produce the image of the black hole or to measure decay of quarks or whatever. So when we talk about theories and models and evidence, it seems arguably that we're talking about these things as being shareable products. These are products that are shared by many individuals. But that is in conflict with this sort of individualist view, right? So on the kind of on this individualist view, we're saying, okay, in order to take the products of science as being representations, we can only specify the target of a representation. We can only specify what the representation is when we're thinking of it as being something that is just in the head of a specific individual or in the mind of a specific individual. And then we can ask them, like, well, what is the target of this representation? What does this thing represent, right? So what does this fMRI image represent? I can ask a specific individual. So that's in conflict with our desire to analyze science as a collective activity. So on the one hand then, so here's the dilemma, right? On the one hand, taking the products of science as representational seems to commit us to this extremely individualist view of science, but there are general reasons why that's not a particularly appealing perspective on science. On the other hand, if we take the products of science as non-representational, well, that seems to undermine realism, right? If there's just if the fMRI image isn't representing anything, then we can't say whether it's accurate or inaccurate, right? Like an fMRI image can't be an accurate image of a brain if it doesn't represent a brain. A particular model, like in the sense of a set of equations or something, that can't be an accurate model if it doesn't represent anything. Like if I have a set of equations and I'm saying, okay, this is a model of the sun, well, I can now ask, is this accurately depicting the sun? Is this giving me an accurate picture of what the sun is like? If the model is non-representational, then it just doesn't have a target, so there's nothing it can be right or wrong about. Yeah, there you go. There is the dilemma that So the first horn is we can take the products of science as being representations, but then that's going to commit us to an individualist, what I'm calling like an individualist view of science, which is unappealing. Or we say that the products of science are non-representational, but in that case, it doesn't look like we can be realists. And that is the dilemma. And that's all I have to say. So that's that. Okay. Thanks for watching.